Hello, I'm Jonathan Platt, a senior member of the Alabama Astrobotics electrical team. Throughout my time at the university and on the astrobotics team, I have been exposed to many STEM skills, but one that sticks out to me is modeling and simulation. Today, I'm going to go over some basic antenna modeling in ANSYS HFSS. Although this isn't something that we do much in astrobotics, the 3D modeling skills and overall thought process used are transferable to astrobotics and beyond. Before we dive into the modeling, I should probably tell you a bit about what ANSYS HFSS is. ANSYS is a software development company that creates state-of-the-art simulation packages for everything from structural analysis to fluid dynamics to electronics. HFSS, or High Frequency Structure Simulator, is their 3D electromagnetic wave simulation package. It is used by many industry professionals for lots of different purposes. We'll specifically be using it to verify an antenna design. The type of antenna we will be modeling is a horn antenna. This type of antenna looks and behaves like a megaphone for electromagnetic waves by focusing them in one direction. Thus, the amount of energy directed in that direction is higher, allowing the waves to travel further before they dissipate. Specifically, I will be modeling a cylindrical horn antenna, since they tend to be easier to build, and its rotational symmetry means that it is not an issue if it is mounted slightly off axis. It will operate around 1.42 GHz, since that frequency is of particular interest to radio astronomers. So here we are in ANSYS Electronics Desktop 2019 Revision 2. You can see that when you first open it up, you usually don't have a project and you have a mostly blank window. So first thing you want to do is create a new project. And then we're going to go ahead and make it an HFSS project. So now you can see we have the modeling window here on the right. And then the left mostly has this tree, which just has some of the different parts of our simulation and model. So jumping into the modeling, there's a lot of different ways that we could go about creating this. The way that I'm going to do it is take advantage of the rotational symmetry that we have in our antenna design, and I'm going to essentially create a cross-section that I'm going to rotate around this y-axis. So the first thing I'm going to do is just orient ourselves on the front. And then the next thing that I'm going to do is zoom out to make sure that we're on a scale that is appropriate for our model, just so that we have a good visual of it. And now I'm just going to get started by drawing the lines, and I'm just going to start with the rough overall shape. So right now I'm doing the rear cylindrical part, and then now I'm doing the conical part. That was the front of that cylindrical horn antenna. Now I still have a line. To get rid of it, I'm just going to click in the same spot, and now we've finished with that. Of course, that was just a rough overall sketch, so now I'm going to go in and define each of these. So the first thing, one that I'm going to look at is that first line that we drew. Obviously, we want it to start at the origin, but we don't necessarily know exactly how tall it is. Right, this isn't set right. So right now it says 160 millimeters. Instead, I'm going to define that to be what we want. And to make it easier to change later, I'm going to use a concept that you can see mostly in ANSYS, but in a few other simulation and modeling packages. I'm going to use some variables. So I usually start them with a $sign, and I'm going to do diameter, since that is actually going to form essentially actually the radius of the cylinder. So I'll do diameter over 2. And now it's going to ask me what I want diameter to be. And so I'm just going to go ahead and set that to be 148 millimeters. And that'll take care of the units. And you can see that that did slightly change our model, but we're still on track. Next, we can move on to this next segment. You can see that the first point has already been updated. So now we'll just look at the second point. We still want it to be flat, so the second, or the final point, which will be the z value, We still want that to be diameter over 2, but the Y position, that is going to be determined by what the cylinder length is. So I'm going to go ahead and call that sil length, just to be a little bit of shorthand. And that value was calculated out to be 110 millimeters. So now that we've got that in, we can move on to the final point, which is going to be a little bit more complicated since we want to define this based on the length of this line segment and the angle, just to make it easier to change in the future if we have any other revisions. So the way that we're going to do that is actually just by starting with this previous set of values and then adding on the other additions. So essentially getting a relative to that last position. So the way that we're going to do that now is for cylinder length in the Y position, we're going to add onto that the length of this diagonal section, and we're just going to go ahead and call that cone length. So cone len, and we're going to multiply that by the cosine of the angle. So cosine, we can just do functions right in these dimension definitions, and then we'll call the angle cone ang. So that takes care of the y dimension. Now we'll go ahead, and it's very similar. You'll see we're going to do cone length times, and here we'll do sine just of that angle. That will be cone ang. Now it's going to ask us to define those variables. So the cone length we determined, or was determined ahead of time, to be 485 millimeters, and the angle was determined to be 30 degrees. So now we have this overall, we have this cross section. We can go ahead and highlight that. And here we can see that it's sweep around an axis. Pick that. We want to sweep around this y-axis. We'll go ahead and do that. And now we can see we have the overall conical horn antenna shape. And it looks sort of like what you might think a speaker or a megaphone would look like, and that's for good reason. The next thing that we want to do is add some thickness to this to make it a three-dimensional object more than just a surface. So to do that, we can go into this sheet and we can pick thicken. We're going to take advantage of variables again, and we'll use $ thickness. And again, that'll allow us to more easily change it in the future. And we'll go ahead and call that 0.5 millimeters, just since that is relatively common thickness for sheet metals that we would be able to obtain should we want to manufacture this antenna. Now that we've got that out of the way, we want to think about an actual material for the antenna, because right now it just defaults to being made out of a vacuum, which doesn't really make sense since that's the absence of material. So we will go ahead and assign a material, and we're just going to do aluminum since it's a common material and it won't have too much of a negative impact on overall performance. So we select aluminum, and now we see that it is properly defined. Now we need to go ahead and put in the actual part of the antenna that either receives or transmits the signal. Since most of the structure is just used to shape the electromagnetic wave, we need to put in that source. So the location that we're going to do that is right at the back of the conical antenna, or the cylindrical horn antenna. And that's, again, much like you would think of a way that a megaphone would work, just based on your intuition. So we're going to tilt it, and now we can see there we're going to set our drawing direction to be in the XZ plane, since that's where we want to be drawing. And we're going to go ahead and click the circle tool, and we're just going to fill in this whole backspace with another circle that we're going to set as our source, essentially. We're going to go in and use that same diameter over 2 variable definition. So that's another advantage of using variables. You don't have to remember exactly what the number is. Now that we've done that, we can take this and assign excitation, which is essentially what our source is. And we're going to do a wave port, since that goes with what structure we've chosen. We can just leave all of these as the default setting. Again, we can leave these as the default. Now we need to go ahead and assign boundaries to our structure, and that just lets our simulation know when it can stop simulating, because obviously we need to account for some of the area outside of our antenna, but we can't just keep going on forever. So there's a quick way that we can do this by right-clicking on what corresponds to our structure within this tree and create open region. And we assign the frequency that we want, since the distance that we need to go from the antenna depends on the frequency that we're operating at. So as I mentioned, we're doing 1.42 gigahertz. We'll set that, and we can see that it makes this nice box around our model. One last thing that we have to go ahead and do is go in HFSS, radiation, insert far field setup, infinite sphere. And this is just useful because it allows us to get some other properties that are essentially how this antenna looks if you were really far away from it. And that's important to us since we want to use this antenna for radio astronomy. And so obviously all of the stars and radio sources we'd be looking at are extremely far away. Once we've gone ahead and done that, we need to set up our analysis. So we'll go in, add solution step, and we're going to do advanced just to set up exactly what we want. We can leave the name as default. We're going to go ahead and do 1.42 gigahertz again. And neither of these settings need to change for what we'll be working on, but if you want to get a slightly more accurate, you can increase the number of passes or decrease maximum delta S. Then we will go ahead and hit OK. And now we're good to go ahead and simulate. So we can go into simulation, validate our simulation to make sure that we put in everything we needed, and then we can pick Analyze All. We'll need to save the file to somewhere. I'm just going to pick the desktop, and the default name is fine. All right, and this could take a little bit, so I'll cut back to once the simulation finishes. All right, it's a bit later now, and it looks like the simulation has finished. So we can go ahead and create our results files and then begin looking at them. So in order to do that, we right-click on this results item in the tree, and we go to Far Fields Report, since again, we're most interested in the behavior from how the antenna looks from really far away. And we'll go into 3D polar plot, and this is going to allow us to see how much amplification the antenna is going to give us at different positions around the antenna, essentially. So in order to do that, we look at the gain, and it's common to just set it to be in decibels, since that just makes it easier to understand what's going on. So we go ahead and click New Report, and the results file will pop up. And so we can see here that directly in the front of the antenna, where my mouse cursor is, we're going to get just under 20 decibels of gain. So we can actually see right here, it says max of 16.2. And essentially what that means is that that's how much gain we're going to get relative to an antenna that senses equally in all directions, because the antenna can't actually make a signal more powerful, but it can be more directive, allowing us to receive more power from a certain direction. So it's always a trade-off in that way. And so this 16 decibels, actually we can convert that into a ratio that tells us how much stronger it is than a normal or an antenna that is equal in all directions. So in order to do that, you divide the 16 by 10, and then you raise that to the power of 10. And so that's going to give us a relative increase of about 40 times more powerful. And so we can actually go ahead and see that if we modify this to not use any function, and we can see that the max is around 41. But again, using decibels is very common, and it allows us to better compare against different antennas. If you're not sure exactly how this corresponds to the antenna, we can actually right-click on the plot in the tree and do Show in Modeler window. And that will let us see, once we open up the modeler window, it shows us that that big red powerful region is going to be right in the front. And then some of those smaller regions are in the back where we wouldn't really expect to get any signal at all. Another really interesting result that we can see occurs if we go into Create Far Fields Report and we do rectangular plot. And so what we're going to do here is say that we are interested in seeing how quickly the power drops off if we were to tilt the antenna from left to right using this phi angle. So we can change the sweep to be phi, and if we're not really interested in any of the theta angles except this most powerful one, we can just go in and select the most powerful one, which we can see is about 90. And again, we're going to be looking at gain, and we'll put that dB function on again. And so here you can see we're getting the phi versus that gain in decibels. And again, we're seeing the most powerful seems to be around 16. We can get the exact value by adding a maximum marker. And again, we're getting that same 16.16 value. But say we're interested in seeing, again, how quickly it drops off to one side or the other, we can actually add a marker, a Y marker. And we can see that if we're willing to accept maybe only 10 dB of gain, we can have an angle anywhere between 70 and 109 degrees. So that's approximately 20 degrees off from that central 90. Normally we're going to look at the 3 dB drop, so that would correspond to about 13.2. And if you do the math, that actually means 3 dB drop corresponds to half power. We're going to get half of our overall power at the half of our overall gain between the angles of 77 and 102 degrees. So that's about 13 degrees in either direction. All right, I think that's about all I had time for today. I want to thank you for watching, and I hope you learned a little bit about STEM, modeling, and RF. This has been Jonathan Platt with the Alabama Astrobotics. Thank you.